My name's Scott Woudenberg. I'm a product manager on Google Cloud, and today we're going to talk about a little bit about architecting for performance when you're building large-scale applications in the cloud. Just a quick process note, I think you've seen these slides probably on some other talks, but this session it has a dory, so you can pull up the app, like the Google Cloud Next app, click through, find this session, click through to the dory Q&A, and submit questions like kind of throughout the session, and as you think of them, rather than trying to remember them till the end. And we'll have at the end, the Q&A session, we'll take questions both from live questions from the audience. There's microphones that you need to come up to, and we'll alternate between that and the dory if there are questions on the dory as well. So just keep that in mind, and let's get going. So just give you a little bit more info about what I'm going to cover. I'm going to start with a little bit of discussion around the state of what Moore's Law looks like today, how the trend's been going the last few years, what the implications are for scale-up applications or applications that depend on scaling vertically. We'll also talk about what kind of challenges get introduced and you have to start dealing with when you start re-architecting for more scale-out type applications and tracking performance in those types of systems. And we'll do a real-world example or talk through some examples from real-world application, which I'll talk about it when we get to it. And then at the end, we'll kind of cover a little bit about, once you've kind of got your performance well understood, what kinds of things you can think about next and kind of optimize for and that sort of thing. So this graph kind of shows the Moore's Law. Like, kind of the big question is, like you've seen articles, Moore's Law is dead, a bunch of information around that. Is that technically true? Well, if those who remember, Moore's Law is about transistor count doubling every 18 months / 2 years, depending on who you talk to. So you can see from this graph, like transistor count continues to go up. So that part of Moore's Law is not really dead. But some of kind of the important characteristics that also used to scale along in roughly that frequency are no longer holding. And so, for example, like kind of single thread performance, like as measured by like your typical spec-int CPU type benchmark, continues to increase, but not nearly at the same rate as it used to. The frequency of the CPUs themselves, as well as the power that they can actually draw, has sort of plateaued off. There's some reasons for that. It's called the power wall. It's pretty easy. It's basically about getting that much power to a small area of the chip, the small die area, without basically melting the whole thing. And then the number of logical cores continues to increase with the transistor count, which is good. But that kind of signals, even at the CPU microarchitectural layer, they're already kind of moving away from the vertical scaling, super high frequency, higher and higher frequency, to more of a scale out configuration architecture where they're just adding more and more cores, and so taking advantage of parallelism at the CPU level to get more performance out of the same amount of power. So how does this impact like large-scale application architectures? Basically any of scale-up components that you have become your performance bottlenecks pretty quickly, especially as if you're building a service that serves, it's a mobile app or something that serves 10,000 users, you can probably do that on one SQL database running on one VM. If you scale that up to like 100 million users, that's going to fall down pretty quickly. So large-scale application developers or people that are trying to evolve their architectures to support a larger, very fast-growing user base are having to, figure out how to re-architect their scale-up components and systems to be more horizontally scalable or scale out. So examples include like sharding your user base or your users across multiple shards of a database, maybe geo-specific. So you run, all the users in Europe are in one database, all the users in the US are in another database. That's one example. You can do the same thing with front ends, like you kind of build, get rid of the state that sits in your front ends and do scale out, like you run multiple front ends to terminate your inbound client connections and things like that. But all of this also means that as you've changed the architecture, your system becomes a lot more complicated. It gets a lot harder to understand and reason about what the overall system performance looks like and how to troubleshoot that. There's a good analogy to if you think about like high availability, building high availability systems, you got to have redundancy. You want to get rid of single points of failures. You can kind of use a similar analogy for your when you're thinking about performance of your application or workload. In that, if you've got a scale-up component, that becomes a single point of a performance bottleneck. Doesn't quite roll off the tongue like single point of failure, but it gets the point across and kind of gives you a good mental model to keep in mind. So, kind of going for a quick example, if this is just a basic web browser, right? It's just serving some content, and you've got two variations. Like you've got on the left, you've got one that's where the database and the web server and all the tools and everything are sitting on one machine. It's pretty easy for me to measure like total QPS or total requests per second that I can process here. I can use my standard operating system tools like on Linux, like top and whatnot, to see what system, like is the database the thing consuming all the CPU? Is it my web server or whatever? So that's pretty easy to understand and figure out where your bottlenecks are. And even in the example on the right, where you've kind of split that out, you've now got two machines, one that's dedicated just for the database and one that's then running your web server tools. You're still, you've only got two places to look to kind of figure out what your performance, what's currently limiting your performance. So, as my number of connections grows, do I see a plateau? Well, I need to go look at what system is the thing that's causing that and how to architect to fix it. On the other hand, if I'm building something quite a bit more complicated, like this is an example of a real-time ads bidding application, at what point or where if my bids per second are hitting a cap or the latency of each bid is increasing as my number of bids I try to submit goes up. How do I know where in here the bottleneck is? It could be maybe it's at the load balancer, probably not. It could be I'm not adding enough compute servers, the bidding servers. I might not be quickly scaling and adding enough of them. It could be kind of many of the different components here, and so understanding which one it is becomes a lot more difficult. And then once you kind of, not just performance of your application, but also, am I spending too much money to deliver this? Like, how do I, if in a system like this, what's the most likely, this is genomics analysis, so you've got a bunch of gene sequencers that are, doing a gene sequencing analysis, dumping all that data into VMs to ingest into this big HPC cluster that also runs on VMs. Of all these systems, which one is probably the most likely that I'm overpaying for, or that I can, optimize or tune to be more efficient, or maybe try a different type of hardware component, optimize my computation for GPUs, for example, and if I can get more throughput that way, that might end up being cheaper than continuing to add more CPU VMs. So that's just another example. So earlier I said we were going to talk through some examples from the real world, because I think examples really help kind of cement these ideas. And I'm going to use examples from Compute Engine itself, which is the service that I work on, and it's an infrastructure as a service. We rent VMs by the second, and it's basically it's a very complicated, complex service. Got a lot of different components: control plane, data plane, actual VMs, the underlying host machines, KVM, host kernel environment. Lots of different components to think about. It's also got lots of customers, and it's growing pretty rapidly. So we're having to re-architect different pieces as the service continues to grow, and kind of identifying which pieces those are, and is kind of part of this whole process. And then there's obviously a huge variety of use cases, infrastructure, so people can use it for whatever they currently have, want to run, want to build. So there's a lot of different use cases, a lot of different requirements, different performance characteristics that different applications need, and et cetera. So, and this is kind of the journey that we've been on, since we launched the service many years ago at this point. And so providing examples from this, I think, will help cement it. So kind of the step one for any kind of performance analysis that you want to do on a complex system is measure everything you can think of. We think in terms of what are called service level indicators, and essentially a service level indicator is simply a metric that you want to track, like number of VM exits, for example, or plus add the reason for the VM exit, cache misses, TLB misses, like that sort of thing. Those are all SLIs that you can figure out how to measure, and then start
start analyzing over time and build dashboards around and start correlating with potentially performance issues that your customers have. Those are examples at the VM level. Higher up in the control plane stack, like latency of API requests. Like every time an API request comes in for creating a VM, how long does that take before I can respond back? Like, and how long does it take for the VM to spin up, and that sort of thing. So these are all examples of kind of the service level indicators that are important. And a good mental model is, ask yourself, what performance related things do my customers care about? Like, do they care about spin up time of a VM? Probably. Do they care about, the number of TLB exits? They probably don't know how that affects their performance, but if they have a performance problem, we could use that to help troubleshoot it. So that's another good example. And just to kind of give you some numbers, some examples, you're probably not going to start out quite this big, and we didn't start out this big either, but just the jobs that run the virtual machines themselves export over 6,000 of these SLIs, like basically every few seconds. And so we have a massive number of these that we analyze and collect. And 2,200 of those, of that 6,000, just come from the virtual machine monitor itself, like the process that is sitting there kind of monitoring the VM and what it's doing and helping do the I/O operations and things like that. So, you won't start that big, but it's pretty easy to get that big if you're building a complicated system. So here's an example kind of I referred to a little bit earlier, like creating an instance. This is probably one of the most important, operations that a service that sells VMs is doing. So customers tend to care a lot about it. And when we measure this graph is actually from an internal dashboard that we have that measures this kind of constantly. So the vertical axis is how long it takes to create the VM, basically from the time the compute engine receives the API request to when the guest OS finishes booting, because we have a signal for that it hits the metadata server, and that's how we tell when it finishes booting. And then over like the horizontal axis is just kind of over time. So we've been measuring this for many years, and so this kind of I just took a snapshot of this dashboard for a few months. I think it's over like a 6-month period a while back. So once I've got a lot of metrics that I'm gathering, what do I do with them? So the next step is to set targets for what those metrics should be. And we started with service level indicators. That's the raw metrics themselves. Now we talk about service level objectives. And service level objective is basically like, all right, well, here's what I'm measuring for, let's say, VM create time. And it's on the order of 35, 40 seconds. That sounds good. Is that good enough? Do I want to set my SLO at where I am today? Am I getting customers that are already complaining that my VMs take too long to spin up? Maybe that is a good signal that tells me, well, where I am today is not maybe where I need to be, so setting the SLO more aggressively and then figuring out what I need to do to hit that is definitely a good way to go about it. Many of you will probably, if you've read the SRE handbook, you'll probably recognize some of these terms that I'm using, SLOs, SLIs. These are all metrics that our SRE teams use for availability of a service as well, and they map very well to performance availability, if you can think of it that way. Like, is my performance consistent, and is it at what consistent level am I delivering it? What happens when I fall out of that, et cetera. So you set the objective. Your customers can help tell you when or how to set that objective or what to set it to. And if there's no obvious target and you haven't gotten any complaints about a particular performance characteristic, it's probably fine to set the SLO where it is today. And then when you start getting feedback from customers that it might not be good enough, then reconsider where you would set it. Another key thing about SLOs is you have to have like kind of a similar, there's a lot of details in the SRE handbook about this as well, but you have to have a plan of action for either if I set my SLO at a better target than where I can deliver today, you need to have a plan to get it to that new target. You also need a reaction plan if you set it to roughly where you're delivering the performance today. The reaction plan is, well, what happens if all of a sudden I stop meeting that SLO? Like, let's say I did a push of a new binary or a new component of my system, and all of a sudden my VM create time goes below SLO. I have a certain amount of time to react to that. That's my SLO budget, and the reaction plan really needs to be very quantified. For something like VM create, if we go from creating VMs in like 30, 40 seconds to create it taking 5 minutes, that could break many customers' applications. And so it's critical that the plan be immediately actionable. Like if it was a rollout, then roll it back. Like get back to the state where we're meeting SLO again, then go figure out what went wrong, go fix the bug that in that push, whatever the case may be. So that's essentially the purpose of the SLOs and the importance of having like kind of that scripted action plan ahead of time, because if you don't have that and the first time you go out of SLO, you're scrambling to try to figure out like what you should do. There should be a really, really established playbook for that. So just kind of give you a visual, example of creating the SLO. We go back to the create instance example, and essentially you're like setting the SLO is like drawing a line at where I think is acceptable for create performance. And obviously, since the vertical axis is time, lower is better for VM create. That means VMs are getting created faster. So the other lines are actually some of our internal systems that we measured, like different components and different flows of our internal provisioning and resource allocation systems, and so that's why this graph has a lot of different bars on it, but that top bar is the one where, that measures when the guest OS is finished booting. The next step of this whole process is basically go back to step one. Like you are gonna do this over and over and over, especially as you're iterating on your application, your user base is growing, you're finding these new architectural limitations or scale-up components that are currently your bottleneck. You're reevaluating where you have set SLOs because customer reported that they had an issue at such and such a time. You go back and look at what your telemetry says, and we were within SLO. Maybe that means we need to change the SLO and start figuring out how to do better. So it's if you get enough customers that are complaining about a specific thing not working well enough or fast enough, that's usually a really good sign that you have to readjust and rethink that SLO. And basically, you have customers. As your customer base grows, you're going to be doing investigations with them. They're going to have issues. You're going to go look at your telemetry. You're not going to find anything that is measuring exactly what it is that's causing them the problem, and so you're going to work with them on a repro, you're going to have them repro it, whatever the case. You'll eventually start adding additional SLIs, defining new SLOs, et cetera. So this is a very iterative process, and will continue as new investigations go on, new troubleshoot with customers, you'll add new SLIs, set new SLOs, but at some point that kind of process stops, and you are no longer finding new things to add, but you're still encountering customers having issues, and it's basically your telemetry, your internal telemetry has taken you as far as it can when it comes to measuring what the customer performance is. And at that point, you have to become a customer of your own service. So essentially, you want to build your SLIs in a way that it directly reflects what the customer sees. And a good example of that is my original metric was time to when the guest OS finished booting. That's not the whole story. Most customer applications, most users, if I'm SSH, they don't care when the guest OS finishes booting. They care when they can actually get access to it or it can start serving. So probably needs network to be provisioned as well. So that's basically a better customer-facing metric is when from the time we receive the API call to when you can SSH to it. And those new lines that you see, that orange line in the middle, that was the original guest OS boot line. And I've just added the network provisioning steps and network path programming, internal and external network programming and all that to this graph. And funnily, comically enough, I don't know, it wasn't funny at the time, but this was when we learned that our network provisioning time scaled roughly with how big our service was getting, and figured out that we have to go fix that and re-architect network programming model to make sure that doesn't happen. So again, you get really interesting signals when you start measuring from the external customer's perspective rather than just relying on your internal SLIs. So that's basically what we end up having to go do is we built a service that measures performance just like the customer. So it runs benchmarks, it can run workloads. It's called PerfKit Benchmarker. It's open source, it's on GitHub. You just search GitHub for PerfKit Benchmarker, you'll find it. There's also PerfKit Explorer, which is a basically dashboarding and analytics framework that makes it easier to kind of build graphs, kind of like the ones that you saw in some of my examples. And you start using PKB or a PKB-like service. So it depends on whatever your service is, but you basically end up building something that measures the performance like your customers do. So if it's a mobile application, you are probably gathering telemetry out at the client end, you're like running tests that mimic client behavior to connecting to your servers. Maybe you do it on actual mobile devices, maybe you do it on emulators, whatever the case, but having an automated framework that lets you launch these tests and rerun them constantly in all of your environments, including your pre-production environments like your developer environments, your staging environments, those become critical to catching issues, regressions, SLO violations, et cetera, as you develop and build new versions of your product or application. So it's the key with the measuring your own service. It's a prober-based system. So you're probing from the perspective of the customer. So in the VM, like in the example before, we were probing by basically running a service that measures when I can SSH to the VM. So that means I run something inside the VM that lets me know when that succeeds. And a lot of the prober-based benchmarks are the same way. You spin up a VM, you install whatever benchmark you want to run, you run it, and then you collect the results back and graph the results and see how things are going. So now we'll do a quick demo. Can you flip over to the demo? Cool. So I'm going to run, the demo I'm going to run is TCP round robin, which is basically, it's part of the PKB suite, but it's a net perf benchmark that measures the VM to VM latency, like latency round trip latency between two virtual machines. So I'm just going to kick off the demo first, and then I'll talk a little bit about what it's doing. It takes a few minutes, so I'm going to have to dance around while it's actually running. So let's quickly take a look at the actual script itself. All the script is doing is basically calling PKB, which is the main kind of orchestration script. And gives it a bunch of arguments. The key, one of the arguments is netperf_config.yaml. So I'll pull that up in a minute. But basically, once PKB finishes its runs, it collects all the data in a local directory, runs a plotting tool that creates a nice CDF, and then uploads the CDF to a storage bucket, which I'll pull up as soon as it finishes. So the CDF is basically just a graph that shows the distribution of what the performance looks like. So it's a cumulative distribution function. It's a really nice way to look at like what my average performance is, what my long tail performance is. It kind of shows you that graph, and I'll show you in a minute. It'll make more sense. Couple notes about the benchmarks themselves and kind of the guidelines around this. Actually, let me quickly pull up the config file. So it's pretty straightforward as well. All it's saying is I'm using N1 standard 2 VMs. I'm using the internal network to do my measurement. I'm not going out through external IPs. The benchmark I want to run, how many buckets, histogram buckets I want to collect for it. And I actually ran the multi-zone argument, which means it's spinning up 10 pairs of VMs in 3 different zones across 3 different regions and running the tests, running the RR benchmark for 60 seconds on each pair of VMs to measure, to get a good sample size of the round trip time between VMs in those zones. So let's see how it's doing. Cool, yeah, it's still running. You can see it's SSHing in to the VMs, running the tool, and it'll be pulling the data back. So kind of talking about a little bit more generally about benchmarking, how to pick your benchmarks that you want to use. Micro benchmarks are usually a good start. Micro benchmark like spec int, spec CPU, core mark. TCPRR is actually also considered a micro benchmark, but it's a little bit more representative of what an actual real application might want to do, or a performance characteristic that might be valuable to understand for a real application. Micro benchmarks in and of themselves are not always a good indicator of what your workload is going to experience. Like workloads tend to be a lot, like real workloads tend to be a lot more complicated than that. And so you can start with micro benchmarks, but you should probably have a plan for doing something that's more like, running things that are more like what your customers are running. For GCE, that includes running benchmarks and micro benchmarks in combination. So maybe I'll fire up, spec int or core mark or whatever, and at the same time, I'm also spinning up like a net perf to do some network traffic, TCP stream maybe to push a bunch of network either out to the internet or some internet endpoint or between VMs. Might also spin up like an IO stat or FIO benchmark at the same time, which is hammering on my storage, whether it's local SSD or PD or what have you. So now I've got the VM actually doing a combination of things, and I can start really getting a sense for, oh, well, when I start doing a lot of disk I/O, this other thing, my CPU benchmark slows down for some reason. You should probably go understand why that is, because chances are customers are probably going to be doing things more complicated than just running one, CPU-heavy benchmark or CPU-heavy, workload. And then better yet than combinations of micro benchmarks is actually workload-based benchmarks. So, you can get a sense for GCE, we know lots of customers run NoSQL databases and Apache, LAMP stacks for web serving and stuff like that. So there are open source benchmarks out there that will measure the throughput of a Cassandra cluster or like a MongoDB cluster. Aerospike's got a great set of test tools for their NoSQL database, in-memory NoSQL database. So find the benchmarks or find the workloads that your customers are running, even if it's just a piece of it, and start measuring those. And then the better still is when you actually can run exactly what your customers are running in exactly the same config, and that's not always possible. For us, we sometimes can, we sometimes can't. We can get a sense for what they might be doing, we'll have a meeting with them, talk about what they're doing, and then try to replicate that experience in our own environment using similar configs. Sometimes we actually can work with them and get the benchmark or get the workload that they're actually running, get a copy of it, and they just give us a bunch of dummy data, and we can do the same exact thing that they're doing, just with data that is kind of placeholder. So. All right, cool. So it finished. It took a few minutes, so I managed to cover the time. So I'm just going to go to the GCS bucket now, refresh it, and you can see the timestamp on it is just a few seconds ago, and so it actually worked. Woo, demo gods smiled upon me. And so this is what I was talking about, CDF. So this shows you, what the distribution of latency of your VM to VM latency is in 3 different zones that we have that are across 3 different regions. And so like kind of the 50th percentile, this is like your average median round trip time between VMs. And then you can see like up toward the top, some zones are slightly better in the long tail than others. But the more vertical this is, the better. And so this is pretty good indicator. Things are working reasonably well here in these zones. So, okay, we can flip back to the. Cool. Let's see. So, okay. So now I've got my SLOs defined. I'm meeting them all. I can catch regressions in new versions of my system before they hit production. What now? Like, what's kind of the next step from here? A lot of that then becomes turning your focus toward making your systems more efficient. You're probably, got a backlog of some re-architecting you need to do depending on how fast your customer base is growing, your users, or how your user base is growing. So, am I spending way too much money on solving this problem? Is there something I could be doing more efficient? Is there some product that I can use that gives me a better TCO, like a total cost per whatever it is I'm trying to do? And kind of to that point, it really helps to start thinking about what is your cost for performance. So, like, what is it costing me to hit, for example, that like the 30-second create time for VMs? Like, how much more would it cost me engineering investment-wise, resource-wise? Maybe I can shard my control plane even further to let it scale up further. What's that going to cost me to get another 10 seconds off of my VM create time, right? So thinking about the performance cost and cost of the performance that you're trying to get and how much it would take to get to the kind of the next level of performance really helps with this process. Another example is if I'm doing ML image training, I'm training a ML machine learning model to do image recognition. During the training, what's my pennies per image, right? Like hopefully it's not even pennies per image. If it is, you're probably doing it wrong. And then once you've got it trained, what's my classification cost? Like what is it? How many pennies per classification am I spending? And can I do better than that? So, kind of find the products that fit your patterns, what you want to do. These are some examples for GCE, but this is, I think this is fairly generally applicable. You want to find discounts where you can get it. So like for our committed use discounts are really good for any time you've got like kind of a steady amount of workload, like steady number of VMs. If you buy committed use discount that kind of covers the number of resources that you're using for where the green line is, you're getting a really, really good discount up to like 57%, I think, discount if you buy a 3-year CUD for the cost of that steady state use amount of resources. So it works really well. If you have diurnal workloads, that changes the equation a little bit. But for the steady state stuff, CUDs is a really great way to save a bunch of money. Sorry, too quick, wrong button. Preemptible VMs, if you've just got batch style computation that you need to launch a bunch of VMs, do some computation, then just delete them all. Preemptible VMs is a great model for that. They're 80% cheaper than normal VMs, and as long as you can handle, if you've got a worker-based system that can handle a worker going away, remembers what work it gave to the one that just died and gives it to another one, this is a really good way to save a lot of money as well. Custom machine types, it's another feature that we have for GCE that basically makes it so that you can create your VM to fit your workload, not your workload. Try to figure out how to get your workload to scale up to use the rest of the resources that you have on a fixed shape VM. Other examples, the a la carte config that the a la carte nature of being able to add things like local SSD, different GPUs. You can add that to kind of any machine type or any VM, as opposed to only being able to pick for a subset of VMs. So that's also another way to help save money. If it turns out that being able to run your workload and maybe you find a library that's optimized to do a specific computation against a GPU, and it's like significantly cheaper than doing it on CPU. Like being able to add a GPU to the VM is pretty helpful without having to spend a bunch of money also on local SSD perhaps or whatever else might be attached. So just to kind of recap, what do we start by just measuring everything you can think of? Think about what's important to your customers, focus on that, define the SLOs based on either where your customers are complaining, or if they're not complaining, probably setting them to where it is today is fine. You're going to go through that process a lot. You're going to get customers complaining. You're going to investigate. You're going to find new things you need to measure, new SLOs you need to set. Existing SLOs you need to set higher or lower depending on what you're measuring. And then eventually you'll have to start measuring as your customers do or from your customer's perspective and building a service, or it might not be a service, but that's an conceptual way to think about it. Build a service for measuring the performance of your system as if it's from what the customers experience. So just wanted to give a shout out to some folks that helped me with this. Al Hamill, he runs the performance engineering team. They built PKB. They built the infrastructure to run all that stuff on internally for GCE. He works with all of our, very intimately involved with a lot of our customers, working on analyzing their performance and stuff like that. Eric Hanklin, actually thank him for my demo succeeding because of firewalls and whatnot. And then Brian was one of our marketing people that helped me rehearse, basically, counting my ums.